Hello students, welcome to my class. Today I will teach you how to calculate relative molecular mass and percentage composition. And I'm sure at the end of the lecture you will find how easy it is to calculate. Please check the description box for the notes. So let's straight away begin. Children, before I go to molecular mass, let us just revise the concept from standard 8. So the first topic would be atomicity. Atomicity is the number of atoms in a molecule of an element. So to make the molecule of an element, how many atoms are there? And as you know, they can be monoatomic, diatomic, triatomic, polyatomic, which you have learned. So just to revise with, monoatomic are the elements having one atom in their molecule, like say helium, neon, argon. These are all monoatomic. You can say sodium as well, but sodium, calcium, metals, we take them as monoatomic. But since they are very unstable, which I am going to teach in the later half of this chapter, so we say these are monoatomic, helium, neon, sodium, calcium and so on. Then diatomic. These are elements which are having two atoms in their molecule, like hydrogen, oxygen, chlorine, bromine, nitrogen. These are all diatomic. More than two are polyatomic, where some examples which we have done it last year are ozone, P4, S8 and so on. So here to begin with, please learn the definitions from your textbook, whichever you are following in school. Now the next topic that I would discuss, but very little, will be symbol. As you know, it is the short form that stands for the atom of a specific element. Writing their symbols are based on, as you know, the first letter of its name or the first two, or from its, like carbon, hydrogen, we say calcium, we say sodium, that is from natrium, we say potassium, K from kalium. All these symbols you were asked to learn in standard 7 from the language of chemistry textbook, and they are also given in your textbook of standard 7 and standard 8. So you know the definitions, you know its significance, you know all the names. The next topic would be molecular formula. The symbolic representation of a molecule is a molecular formula. So, if I take examples like ammonium sulfate, ammonium chloride, sodium carbonate. And if you remember, you were taught By which method, if you can remember? It is the Criss-Cross Method, where what you did, you knew that the molecule is formed by a cation and one anion. So when you were given the name, you were writing the cation and the anion, and you were writing the valency on the right top, that is superscript, and you were exchanging. Like I'll show you the example of ammonium sulfate. So you have your cation ammonium NH4, valency is 1 cation. You have your anion as sulfate and the valency is 2 anion. So what you did by the Criss-Cross method, and your answer now is ammonium. The 2 is now the subscript and the sulfate 1 we don't write. I'm sure you have done enough practice on these methods in Standard 7 and Standard 8. You also know how to divide the valencies by their HCF. So let me take the example, say, of zinc oxide. So when it is zinc, Zn. When it is oxide, O, valency 2, cation, anion. When you criss-cross, you have 2. The HCF is 2. When you divide, it becomes 1. So the answer is zinc oxide. You have to take many more compounds and you are going to practice them. Valencies are already learnt, but I will discuss a little about it. What is valency? You have learnt all the names of the cations, the anions, their formulas, their valencies, and you have already practiced the molecular formula. But just to revise, let me take this concept once. So basically, valency is, it is the number of electrons that an atom can lose, it can gain, or it can share. So the number of electrons that an atom can lose, gain, or share during a chemical reaction. Let me give you examples of, suppose I take the example of the cations. Okay, so suppose I take the atom sodium. You have learnt the atomic number of the first 20 elements: hydrogen, helium, lithium, beryllium, boron, and so on. You were asked to learn this in Standard 7 and Standard 8. So let's take the example. We come back to the formation of the cations. That is, we also know how it is that we know about its valency. The atomic number of sodium is 11, and we know the electronic configuration is 2, 8 and 1. Now every atom needs to be stable. In order to attain this stability, it has to lose or gain or share electrons. That is, the first orbit duplet, and after that it is octet. Here you have 3 orbits, 3 shells. This one sodium needs to lose. So by leaving or losing one, donating one electron, sodium becomes sodium ion with now the electrons are this. Actually, it is a univalent example where the valency is 1. Now, the next example let me take of magnesium and atomic number 12, electronic configuration 282, giving away 2 electrons would make it Mg2 plus number of electrons. Now this is bivalent valency 2. So it has lost 2 electrons. The valency is 2. One more of 3. Maybe I will take aluminium. Atomic number 13. Electronic configuration 283. Giving away or losing 3 electrons. It becomes Al3 plus. So 2, 8 and it becomes trivalent. So we saw that when we are just revising with the points, we saw atomicity, we revised with monoatomic, diatomic, polyatomic, giving you examples. We saw symbols, giving you examples. We saw molecular formula, also giving you examples, and the method and showing how you cancel by HCF. We saw valency, understanding, loss, gain or share, and we have now done with cations with sodium, magnesium and aluminium. Now, if I go, this was formation of cation. If I go to the formation of anions, say I take the example of chlorine, atomic number 17, electronic configuration 287. So to attain octet, it has to gain 1 electron and it becomes chloride with electrons 288, 1. So univalent. If you say oxygen, atomic number 8, electronic configuration 2, 6, it will need 2 electrons to give you O2 minus, and the number of electrons are this. This becomes bivalent. So valency 1, valency 2. Similarly, for nitrogen, you can try out yourself. Atomic number 7, electronic configuration 2, 5. It will need 3 electrons and it will become N superscript 3 minus anion. I'll give you one small example of sharing, because we will do more of sharing, donating, accepting in another chapter. So just one example, say we are talking about the compound hydrogen chloride. Hydrogen has 1 electron in its outermost orbit. Chlorine, as we have seen, 17287, there are 7 electrons in its outermost orbit and they are going to share. Therefore, it becomes hydrogen single covalent bond with chlorine 1 Therefore, valency 1, hydrogen valency 1, chlorine valency 1. So we discussed about the loss or the gain or the share of electrons, and we discussed about valency. The next topic I have taken up is valence, variable valency. And this also you have learned, children, like iron, it is Fe2 plus and Fe3 plus. Ferrous, ferric, you have cuprous, cupric, you have plumbous, plumbic, like cuprous, Cu plus, Cu2 plus, plumbous, plumbic, Pb2, Pb4, tin, stannous, stannous 2, stannic 4. So there are some which are having 2 valencies. You have learned it, children, last year. You just need to revise a little. The next topic is radical. An atom or group of atoms of same or different elements that behave as a single unit with a positive or negative charge. Like if I say sulfate. So as it defines in the definition, an atom or group of atoms of same or different elements that behave as a single unit with a positive or negative charge. So you have sulfate, you have carbonate. You have learnt many of this type, children. So just revise it once. We now come to one of the very important calculation, that is to calculate the valency. I just discussed that if it is a compound, it is made up one cation and one anion. So then it becomes a compound. And we make the compound's formula when we know the symbol of the radicals, when we know the valency as well, and by Criss-Cross method we write the formula of that compound. Suppose either the cation or the anion, one of them, the name is not there. Can you calculate the valency of that unknown radical? Yes. There is one method. I would say you should know it properly, where we see how many cations are there, how many anions are there, and which out of the two's valency is known to us. By the formula that number of cations into the valency of cation is always equal to number of anions into valency of the anion. It will become very easy when I show you with one example. Let my compound be XO2. In this formula, my cation is X. I don't know what it is, and my anion is O. I know what it is. And I don't know the formula of cation. I know the the valency of cation, but the valency of anion I know. So let me assume the valency of X to be A. I know the valency of oxygen, that is 2. Now, if I go by this way, how many cations do I have? 1. What is the valency of the cation? I have assumed A equal to. How many anions do I have? 2. What is the valency? 2. So what does it imply? That the valency of A is 4. Thus you have XO, valency 4, valency 2. Cancelling by HCF, your formula becomes XO2. Let me take another example. Say my compound is NaY. I know the valency of the cation 1. I do not know what is anion, so I assume it to be B. Now, how many cations do I have? 1. What is the valency of the cation? 1. Okay. How many anions do I have? 1. What is the valency of the anion? Unknown. I have taken it as B, implies B is 1. I'm sure this example made it even simpler. If you want, I can give you one more example. Let it be X2O3. Unknown, assume, known, we write. Go by the formula. 2 into unknown is equal to 3 into known implies A is equal to 3. What you have to do is, children, you have to take up different compounds and using this method calculate and master yourself in questions like calculate the valency of the unknown radical in a given compound. So now our next topic is relative molecular mass. Now if you remember, last year we have done the definitions of the molecular mass, relative molecular mass, atomic mass, relative atomic mass. So I just need to revise once. Relative atomic mass is the atomic weight, and it is the number of times one atom of an element is heavier than 1/12 times of the mass of an atom of carbon 12. That is, we are talking about the mass of C12 carbon atom. It is 12 units, and when I say C12, it is the carbon isotope. And to say what is isotope, it is the atom of same element, that is having same atomic number but a different mass number. Carbon has 3 isotopes, C12, C13, C14, and here we compare with C12, which we take as the standard. The next one is relative molecular mass, which is the molecular weight of an element or a compound, and is the number of times one molecule of the substance is heavier than 1 by 12 times the mass of an atom of carbon 12, which we take as standard and compare with the atom to get the relative atomic mass, compare with the molecule to get the relative molecular mass. So to begin with the calculations, let us take examples. So the first example can be sulfuric acid, that is H2SO4. So when we have to calculate the mass of sulfuric acid, we have to understand that one molecule of sulfuric acid consists of two atoms of hydrogen, one atom of sulfur, and 4 atoms of oxygen. And to find out the mass of 2 atoms of hydrogen, 1 atom of sulfur, 4 atoms of oxygen, and add them up will give me the mass of sulfuric acid. So here we go. For hydrogen, it is 2 into 1 is 2. 1 into 32 is 32. 4 into 16 is equal to 64, and therefore when we add up the masses of the constituent elements, we get the mass of H2SO4 equal to the sum 98 AMU. So I just repeat the step. You need to know the name of the compound. You need to know the formula. You need to write how many atoms of each type of element are contained in the compound. You need to know the atomic masses. You need to multiply, add up, and get the mass of the compound, which is the molecular weight. Now, suppose I take one more example and let it be blue vitriol. This is crystal. If you remember, there are so many common names, chemical names, and formulas given in your text. You have done it last year as well. You have to learn all those, because many times you will not be given the formula, just the common name will be given, and you should know the chemical name and the formula. So here when I take blue vitriol, the formula is CuSO4 and 5H2O. As I said, the first work is to check how many atoms are there and their masses. So the mass of one copper atom, mass of one sulfur atom. There are 4 oxygen atoms and mass of 5 H2O together we will have to add. So as I know, the mass of copper is 63.5. Some of the masses you have to learn, but mostly it is provided to you in the question paper. Like hydrogen, you don't need to ask, it is 1. Oxygen, you know it is 16. Sulfur, you know it is 32. Sodium, you know it is 23. Some you have already learned, children, but let me tell you, many of them will be provided in the question paper. So come back to the question. So sulfur, you have 1, so 32. Oxygen, you have 4, so 16. And water is 2 into 1 plus 16. So you have 63.5. You have 32. You have 64. And 16 plus 2, 18 into 5 is 90. So when you add, you will get the mass of CuSO4.5H2O, which is equal to 249.5 AMU. I think I am very clear here. Name, formula, number of atoms, masses, add up and you get the molecular weight. Now, your work will be to take up many compounds which is there in your text and calculate and practice, which will always help you in your calculation part. Now the next topic is percentage composition. This is the percent of an element in a compound, and the formula by which we get it is the total weight of the element in one molecule by molecular weight of the compound. So what you have to do is you have to find the total weight of that element whose percentage you have to find out in that molecule by the molecular weight of that compound and then multiply with 100. So here you can get questions like percent sign, of course, sorry. Let me take one question, that is, say, percentage of nitrogen in urea. As I've said just now that there will be many compounds whose formula will not be given to you, children, so you need to know the formula. Urea is NH2CO NH2. Now this contains 2 atoms of nitrogen, 4 atoms of hydrogen, 1 atom of carbon, 1 atom of oxygen. So you have 2 into 14 is 28, 4 into 1 is 4, 1 into 12 is 12, 1 into 16 is 16, and you add up to get 60. So the mass of urea is equal to 60 AMU. Now when you have to find out the percentage of nitrogen in urea, you get, according to the formula, total weight of the element, that is, we are finding for nitrogen, so 28 divided by molecular weight, that is 60 into 100 is equal to 46.66. This goes on, that is 46.67%. You can practice by asking how many hydrogen, or how much is the percentage of hydrogen in water, percentage of oxygen in water. You can even calculate percentage of carbon in urea and go on with the calculations. So I would say now that after practicing, or when you see the video, when you have doubts, if you have any doubts, please feel free to comment below, and I will be more than happy to help you children. So students, this lecture video on relative molecular mass will for sure help you calculate correctly and easily. But you'll benefit more when you are thorough with the definition given in your text, as it is definitely there in the question paper. You are going to be asked questions on that. And most importantly, as I said just now, practice as many compounds as you can, as in to calculate molecular mass, percentage composition, or to write the molecular formula of most of the, or many of the compounds, you can say. Okay children, stay tuned, and please hit the like button, share and subscribe my channel, and hit the bell icon to get notified about the upcoming lecture video.